Hello, my name is Emily Stolfo, and I'm going to give a talk about benchmarking the Elasticsearch clients. It's called Benchmarking Your Code Inside and Out. Before I start the talk, though, I'd like to mention a few things. The first thing is that over the last day and a half, I've gone to a number of talks here, and they've been about optimizing the Ruby interpreter itself, so Ruby itself, about performance, static profiling, the garbage collector. But this talk is taking it one level up, so it's about the code that you write in Ruby and benchmarking that code, so the performance of that code. And just so I can tailor this talk a little bit more to you, by show of hands, can you tell me if you write a language other than Ruby in your job? It can be in addition to Ruby, but a language more than Ruby, or an entirely other language itself. Okay, so that's great, because this talk is about benchmarking concepts and best practices, and I think you'll find that you can apply these concepts to your Ruby code, as well as the code that you write in other languages or other software that you write. So a little bit about me before I get into the talk itself. I'm a Ruby engineer at Elastic. By show of hands, who uses Elastic? Okay, a lot of people do. That's cool. So I work on the clients team at Elastic. The company has a number of different products, some of which have to do with Elasticsearch, but they're all pretty much based around Elasticsearch itself, the server. I work on the clients team, which is the team that develops libraries, gems, etc., that interface with the Elasticsearch server. So handle HTTP requests sent to the Elasticsearch server. And so yeah, I work at Elastic, an adjunct faculty at Columbia University, where I've taught some courses on web development in Ruby on Rails, and a class most recently on NoSQL databases, where I gave a survey of different NoSQL databases, and I talked about different use cases and how you could choose a given database given a certain use case. I'm a resident of Berlin, Germany. I've been there for 5 years. I'm originally from New York, which is why I'm able to go and teach classes at Columbia. It's easy for me to be able to go and stay with family or friends when I want to teach a class. And I'm a maintainer of this list of gems. They all have to do with Elasticsearch, obviously. Half of them are about using pure Ruby with Elasticsearch, and the other half are about using Elasticsearch in the context of a Rails application. So one more thing is that I previously worked at MongoDB. I started at Elastic last June, so it's been less than a year that I've been working there. But I want to mention that I worked for MongoDB for 6 years because it's relevant to this talk. I actually pulled on a lot of my experience benchmarking what they call a driver at MongoDB, which is essentially their client. And it provides some inspiration for what I do at Elastic now. So 6 years at MongoDB and less than a year at Elastic. So first, before we talk about actually benchmarking, let's ask ourselves, why do we benchmark? I think we as humans are really interested in speed and measuring things. In particular, we like to compete and compare ourselves to each other. So I think that it's natural for us to want to measure our code and track it over time and compare it to other things. But when I think about benchmarking and speed, this fable comes to mind, the tortoise and the hare. I think these icons, the tortoise and the hare, are very familiar to us, but I don't know if you know the actual fable itself. And if you don't, and just in case you don't, I'm going to explain it. So essentially, there's a tortoise, which is one of the slowest animals, and a hare, which is one of the fastest animals, and they decide to have a race. And the hare knows that it's faster than the tortoise, so halfway through the race, it stops and takes a nap, because it knows that it can get to the finish line even while taking a nap. But the tortoise is persistent and marches towards the finish line and actually gets there before the hare, because the hare doesn't wake up to his alarm and doesn't have time to get to finish line before the tortoise. So I mention this because I think speed is relative, or the benchmarking is more than just seeing how fast you can possibly go. It's not really just about how fast you get to the finish line, it's how you get there. And we'll see over the course of this benchmarking talk that speed isn't everything. So why do we benchmark the Elasticsearch clients? We benchmark them because we want to detect regression. So as we make changes to the code, we want to make sure we're not introducing any performance implications. We want to detect changes in Elasticsearch that could have implications in the client. So Elasticsearch might change the response format, and that might make the client have to do some extra parsing and then introduce a performance problem. We want to check pull requests. So these clients are open source. We take pull requests from the community, and we want to make sure that they don't introduce any performance problems. Confirm assumptions. So we all code and make assumptions about speed, but they can be proven. These assumptions can be proven scientifically with some measurements. Compare pluggable components. The Ruby client in particular allows different HTTP adapters to be used, so you can compare them. I built the benchmarking framework so that I can compare different HTTP clients used. HTTP libraries used with a Ruby client, and it's not to compete with other clients. So that is not on the list. It's not so that we can, within the clients, compete with each other. So when we talk about benchmarking, we have a bunch of different kinds. I generally think about macro and micro benchmarking, but I have a friend in Berlin who is really passionate about benchmarking, and he also talks about application benchmarking. So this talk in particular is about macro benchmarking. So it has to do with a client and a server. Application is really from end to end, your entire system. It could have n components involved. And then micro is really just one component. So this benchmarking framework that I built at Elastic has three main ingredients. One is my experience at MongoDB. The second is how the Elasticsearch server benchmarks itself. And the third is the Elastic client team experience. So I'm pretty new there, but my colleagues have been able to tell me what kind of performance issues they've had in the past and what to look out for, so what we have to target in our framework. So starting with the first one, MongoDB. MongoDB, it differs from Elasticsearch because it doesn't use HTTP. So it's really important for us to do micro benchmarks because serialization and deserialization is done by the drivers. At Elastic, that's not quite the case. So it's a little bit more important that we look at macro benchmarking, not necessarily micro benchmarking. But at MongoDB, there's a specifications repo that's open source. You can check it out. And it has driver behavior specifications as well as benchmarking framework specifications. And I use this experience as inspiration for how I'd approach the problem at Elastic. And then I also implemented it in the Ruby driver, so I was able to use some of the ideas that I had when I actually implemented this framework in Ruby to my work at Elastic from MongoDB. So the rest of this talk is going to be looking at those two other ingredients. So the Elasticsearch server, how it benchmarks itself, and then how the client's benchmarking framework was built and what it looks like in the Ruby client. We'll look at Elasticsearch benchmarking, client's benchmarking framework, benchmarking best practices, which again you can apply to any language, to any software you write, and we'll look at the code in the Ruby client. So let's start with Elasticsearch benchmarking. The Elasticsearch server team actually has a team embedded inside of it that's devoted to performance. They spend 100% of their time working and monitoring the performance of Elasticsearch as changes are made to the code base. In particular, they have a framework called Rally. It's open source. You can find it in this repo. And what it is a macro benchmarking framework for Elasticsearch. And it's composed of this idea of tracks. And tracks can be thought of as scenarios. They consist of data sets that stress different parts of Elasticsearch, a load generator, so a way to put stress on the system, a way to define what that system looks like, so the cluster configuration, and then define how the metrics are stored, whether they're just printed standard out or they're indexed somewhere. And then it also publishes results. So we'll look at some published results in a bit, and you'll see how useful that is to the community as well as to the Elasticsearch team itself. So a little bit more detail about these Rally tracks. You can find them in a separate repo, Rally tracks, under Elastic, and they're all different kinds of data sets that, as I said, they put stress on Elasticsearch in different ways. So they're rich in different ways. Some have nested documents, some have a lot of different values, different types of values, etc. They all create different scenarios to put stress on Elasticsearch. And it's all open source, so you can take a look at it and actually use it in your own benchmarks. And when I was making this talk 2 weeks ago, an email was sent around from this team saying that someone on the team in what we call space time, which is this special time you get to work on a side project or do something outside of your normal responsibilities. So this email was sent, and it said that he built a UI for people to define their own rally tracks. Because you can define your own rally track. You could before, but you had to do it in the command line, and it was a little bit obscure. But so I wrote to him and asked for his permission to share it in this presentation. And he said, sure. It's not public yet, but I think it's really cool that the performance team at Elastic is going to make a tool available to people so they can define their own scenarios and benchmark Elasticsearch in their own infrastructure and context of their application. So in particular, when I was talking to the Elasticsearch performance team to learn how I should build a framework for the clients team, I took a couple of things from them. That basically, the characteristics that they have is that it's published, open source, they have different tracks, infrastructure, defined infrastructure, and they follow best practices. And in particular, I was really interested in the fact that it was published, what infrastructure they used, and what best practices they followed. So we'll look at those a little bit more in the context of the client benchmarking framework. But first, what the Elasticsearch performance team does is they have a whole Kibana application available to you where you can look at different dashboards and see benchmarks reflecting stress put on the system in different ways. And I think it's really cool. There's a lot of information there, and data has been collected over a couple of years. So it's really fun to check. It's open source. You can look up Rally Elasticsearch and find this Kibana visualization so that you can see what kind of benchmarks they run and how often. Regarding their infrastructure, so Hetzer is a hosting provider. Hetzer, you can use any hosting provider, but what's important that I took from the Elasticsearch performance team was that they had dedicated computers, dedicated boxes to testing Elasticsearch. They weren't dynamic workers, and I'll talk more about that later and how important that is how important it is to have these fixed boxes when you involve a network and network latency when you're doing benchmarks. And then best practices. So my colleague Daniel Mittendorfer, who was most helpful while I was developing this framework. And if you can check out my slides later, and he has a blog post called 7 Tips for Better Elasticsearch Benchmarks. And they cover all of these best practices. He also has a presentation he did last October, I think in Sweden at a conference. And I watched it and I learned a lot from it. And we'll look at these in more detail later in the context of the client benchmarking framework. But if you want to use this as a resource, I would highly recommend checking this out for benchmarking best practices. Okay, so now let's look at the client benchmarking framework and what it looks like. When we set out to build this, we had a couple of requirements. Basically, they were that it had to be published, it had to be language agnostic, because the clients team consists of a PHP client, Python client, .NET, Node.js, Go, Ruby, and some others that I'm probably forgetting, and it's only going to grow. So this framework needs to be language agnostic. It cannot favor benchmarking in any particular language. It has to be open source because we want to follow the model of the Elasticsearch core team. We want to have a common results schema, and we'll look at that in more detail. That means that when we run these benchmarks and we collect data, we have to be able to index them into Elasticsearch in a consistent way so that we can do querying across time and across languages. It needs to have a defined infrastructure, and we want it to follow best practices. So the first step in defining this framework was to look at what the results schema would look like. And at first, when my colleagues suggested that I do this first, I wasn't really convinced. I said, why are we defining the results schema before we define the actual test? But as I started doing it, I realized it actually made a lot of sense, because once you have the result set, the structure of the result set, you can define any test that you want. So that's what we did first. We defined a results schema using something called Elasticsearch Common Schema, which is recently released a GA was released about a month ago. And again, there's a blog post introducing it. So I'll give you the definition of it, and then I'll explain a little bit more. The definition is Elasticsearch Common Schema is an open source specification that defines a common set of document fields for data ingested into Elasticsearch. So what that means is Elastic is kind of an ecosystem. There are a lot of different components, and usually people use more than one. So when events are emitted in this ecosystem and logged somewhere, we want to have some consistent way for those events to be recorded so that we can do analytics on them later. So this Elasticsearch Common Schema defines a lot of different fields and nested documents. And so we use this and said, okay, anytime in the benchmarking result schema that there is an equivalent field in the Elasticsearch Common Schema, we want to use that field so that everything is consistent. So if we have these benchmarking results indexed into a common data source along with the other events in the Elastic ecosystem, we can have a common way of querying everything. So this is what I defined. It's in YAML. This is kind of a subset of what the results would look like. It has three main top-level keys: event, agent, and server. And I know it's kind of small, so I zoomed in on one component. This is the actual statistics. So some of these fields are coming directly from the Elasticsearch Common Schema, and where we needed to save something extra, we would just create a new field for it. But where it can be consistent with the Elasticsearch Common Schema, we are consistent. So using that schema, running a benchmark, this is the kind of result that you would get, and we would index this into Elasticsearch. So taking that snippet we just looked at and we highlighted, that's what the portion of the document would look like. Okay, so we defined the result schema, and we said, okay, we have this basis now. Now let's define the tests. When I went out to define the tests, I divided them into different suites. The first one is simple, then complex, and parallel. Simple, I think of as operations like a ping, a get document, an index single document, a simple search, something that's not expected to take very long and that doesn't involve a list of things. So we have the simple suite, then we also have complex. Complex is something like a bulk request or a more complex query, like on a nested field. And they're expected to take longer, these operations. And then parallel is interesting. Parallel is kind of the inverse. Parallel is a benchmark where you have a given workload and you can do anything you want using threads, other libraries in your language to complete that workload as quickly as possible. And then the result that you collect is the time it took to complete that workload. So it's not really about one single operation. It's more about the big picture. Okay, I got to do this whole slew of work. Let's see how long it takes me to do it, and I can do whatever I can to get there. And including parallelism, if that's something the language supports, that's why I call it parallel. So these are also defined in YAML so that a certain client can decide to dynamically generate these benchmarks based off of a YAML or just manually create them. I kind of dynamically generate them, and I know some other clients don't. They just manually wrote them. But YAML is a common language that we use to document all of these tests. So it's in YAML. And again, to highlight a section, because it's kind of small, this is what indexing a small document 100 times would look like as a YAML definition for a benchmark run. So we have the index, the operation is index. We use a data set called small document, and we define the repetitions. We have 3 warm-up repetitions, 5 measured repetitions, and 100 iterations. Iterations is the number of times you do the operation in one single repetition to reduce noise. So we also have to define common data sets. We have a large document, a small document, and Stack Overflow data set. And as Picasso said, good artists copy, great artists steal. I just stole this from Rally. So if you look at the repo Rally tracks, you'll find that there's a Stack Overflow data set, and you can use that yourself. The reason I chose this one was because the documents are quite rich. There are a lot of nested documents, a lot of different types. The documents tend to be quite large. So I thought that was a very interesting and realistic data set to use to put stress on the system, on the client. Okay, and then best practices. This was very important for us to define from the beginning what are the best practices and how are we going to follow them when we create this client benchmarking framework. So if you remember, some of the ideas I took from Rally in particular was that it's published, there's a defined infrastructure, and it follows best practices. So let's look at some of those best practices, and these are the kind of concepts that you can apply to benchmarking any code that you write. So first, system setup needs to resemble production as much as possible. I love testing the client against Elasticsearch running on localhost on my laptop because it always goes super fast because the network is not involved. But that's not a realistic scenario. So you have to make sure that your benchmarking tests are running in a system setup that closely resembles what most people are doing with your code. In particular, Rally did a lot of the hard work for us and learned the hard way for us, essentially. This is taken from Daniel's blog post and presentation, but this is an example of when system setup, when it's not consistent, it can really affect what kind of numbers you get from your benchmarking. So in this case, he found that the benchmarking results were quite varied and consistently varied. So they were regularly irregular, and you can see what I mean from the graph. And the code wasn't really changing between these benchmark runs. So I don't really know the details, but essentially they had to enable trim because there was a particular process that was running that was basically interrupting the job that was running and affecting the runtime of the benchmark tests. But once he enabled trim, he was able to get much more accurate benchmark results. Second thing is to warm up properly. Warming up was not something I originally defined in the benchmark tests, but I added them in after learning about the best practices, and I said, okay, well, we have to put the warm-up repetitions inside the test definitions themselves so that clients know that they do warm-ups, that they're not just running it once. And warming up is sometimes more important for some languages over others, but I think it's important that we just define it up front for everybody. And if you want to warm up more, that's fine also, just as long as you warm up at a minimum. And so I added the warm-up repetition. So again, zooming in on one of those test definitions, the warm-up I defined as 3 times for this, but if one client wants to do it more, that's fine. So another best practice, model your production workload. Running a benchmark is not about putting the most amount of stress as possible on your system. You can run those tests, but a true benchmark is really making sure that the work you're doing represents the majority of work that people are doing with your code. So that's important to keep in mind because people think that benchmarks mean just seeing like how extreme you can get, but it's really just about a realistic scenario and measuring that. You also have to test your benchmarking software. And if you find me giving this talk in the future and I say I'm still not testing my benchmarking software, please come and talk to me and remind me that I should be. So Daniel says he finds a lot of people don't test their benchmarking software because the output is a precise number. So you have this false idea that it must be doing something right if the number that it outputs is so precise, it's measuring something. But it's important to measure your benchmarking software. In particular, I know the Rally team found that there was a bug in the load generator that was actually creating a bottleneck. So the benchmarking results were not accurate because of this bug. So they're getting some inaccurate readings from their benchmark tests. And so I'm actually not testing my benchmark code yet, but it's coming. Eliminate accidental bottlenecks. So this is one of the best practices that I was really intent on following. I was really passionate about getting this right. And we had a lot of discussions on the clients team about this. And the reason that it was so important for us to discuss this was because we are running the benchmark tests in Jenkins, which is CI, a CI. So we were going to run the client code on one worker and the Elasticsearch server on another worker. But Jenkins has dynamic workers. So we have a number of data centers. So if you do one benchmark run, you could have the client code running in a data center in Norway, the Elastic code running in a data center in Washington, D.C., and then the next run, they could be running actually in the same data center. So what do you think that effect would be on network latency? So we had this big discussion, and I was really intent on network latency being constant. So in talking to the Elasticsearch performance team, I said we have to have the client code running on a fixed box, a fixed Hetzner box, and the Elasticsearch code running on a fixed Hetzner box. Sorry, it's hard to say. and to make sure that network latency is not variable. That cannot factor into my benchmark results. But this is kind of a secret. There's more than one solution. I wanted to know if what my assumptions about network latency being variable between runs if you're using dynamic workers with Jenkins was true. So I actually created a job that runs the client code on a dynamic worker in Jenkins and still connects to the fixed Elasticsearch box. But as I said, it's a dynamic worker, so it could be in one data center in one part of the world and one run, and then another data center in another run. And then you would find that your benchmark results might vary because that difference in geolocation. So the secret is that I created this job in Jenkins to run, and it actually pings this fixed box, and I collect the results from this. And I haven't told my colleagues I'm doing this, but I basically want to confirm that what I was really intent on doing, have these two fixed box, was the right way to do it. But I wanted to see if if we could use dynamic workers. Because, but anyway, well, I haven't collected enough data yet to make any kind of conclusion from this, but it might actually be good enough to use a dynamic worker in Jenkins. I just don't really know yet. But it is important to investigate all of your options and all of your solutions for building a framework like this and make sure you're choosing the best one. We even got into a discussion about what kind of energy Hetzner uses. It uses green energy, by the way, so having fixed boxes running when maybe the client box is kind of idle sometimes in between benchmark runs, not such a big deal. Another best practice, use a structured process. So that means measure things one step at a time. Don't try to do everything at once. And that translates into, this is the definition of the benchmark job in Jenkins, and we say that the triggers are on a commit and daily. So that means that any change to the code base will be measured, so it's one step at a time, not a bundle of commits altogether, and then we also run them daily. And then this is the last best practice I'm going to talk about. Use statistically significant tests. So how does this translate to the client benchmarking framework? So Elasticsearch actually has a plugin called the NOOP Plugin that's in the code base. You can build it yourself with Elasticsearch and use it. And what it is two REST endpoints, NOOP bulk and NOOP search. And what they do, these endpoints, is nothing. Elasticsearch just returns when you hit these endpoints. So if you think about it, if you think about the total time of a request, you have the client processing code, it sends a request, then you have the network latency, and then you have the Elasticsearch work. If you get rid of the Elasticsearch work and network latency is constant, then all you're really measuring is the client code, and that's what we want. That would be a statistically significant test. So any differences in numbers represent a difference in how this code that we're interested in is executing. Okay, so now let's go to the Elasticsearch Ruby Client benchmarking and actually look at the code and the implementation of all of this. It's composed of 3 different parts. The first one is the benchmarking code itself. I'll show it in the next slide. Then there's the Jenkins job, and then there's the visualization. So the benchmarking code itself is their Rake tasks, so I can run them from the command line, and that's easy to do from a Jenkins job. And so I have a namespace simple, and then I have ping, create index, and there are a lot of other ones, and you can actually find it in the repo if you want. And then there are wrappers around the actual running of the tests themselves, and I have them split up into simple, complex, and parallel. And so I instantiate one of these objects, and it knows how to take in a config and run the benchmark, and then it indexes the results. Then the Jenkins job, which takes this code and runs them from the command line, the Rake tasks, is composed of 3 parts. The first part will uninstall any Elasticsearch on the machine, delete the data directory, and reinstall Elasticsearch. Just make sure you're starting from a clean slate. The second part will actually run the Ruby benchmark test. So it'll run those Rake tasks. And I have them grouped into suites, so I can choose to run all of them, just the simple ones, complex, parallel, or just a single one if I want. And then the last part of this multi-job is that the Elasticsearch data directory is cleared out and Elasticsearch is uninstalled. So that's what the Jenkins job looks like, and that runs this entire framework. And it's all set up so that the client code is running on one machine, a fixed machine, and Elasticsearch is running on another fixed machine. So again, network latency is constant and doesn't factor into differences in our benchmarking results. And then for the grand finale, this is my dashboard, where it continues down, but I measure over time different benchmark runs on different operations. So we have ping, index small document, index large document, etc. And so I use this as a kind of heartbeat or a measuring of my code over time on commit and running daily. So future work on this, because I led the project, I'm the guinea pig. I'm the one who has kind of completed it mostly. And so the future work is to have all the other clients implementing this, and we have to figure out how we're going to share that box that we used. We can do it through Jenkins, so it's not so complicated, but we want all of the clients to be doing this, and then we can have different dashboards and maybe compare the clients against each other. That's not necessarily so we can compete, as I said, but that's so that we can maybe identify hotspots in some clients, or maybe I'm doing something kind of weird in my client that's slowing it down, and I can look at how another client is doing it. So it's really to get some deep introspection into your code and how it compares to very similar code, because the clients aren't so different from each other. They're just implemented in different languages. Then the implementation of the parallel suite. The parallel suite has yet to be really defined. It's almost like a phase 3 of this benchmarking framework implementation and definition, because it's so subjective, I guess, and we need to more clearly define how we're going to run these parallel benchmarks and what kind of workloads we want to test, what represents a realistic workload. And that's where I think collaborating with the Elasticsearch performance team will help a lot as well. And then we also want to publish our results. So we want to also have our dashboard available, just like the Elasticsearch performance team does, so that people can look at different clients and not compare them, but just see how client performance has improved, hopefully, over time, and track the work that we're doing. So that is it. Thank you very much. I can take questions if you want, and I'll be around for, obviously, the next day. So if you have questions about Elastic or working in Elastic or benchmarking, feel free to ask me. Thank you. Any questions? I'm going to benchmark your walking up the stairs with the microphone.
Not very good. You had a slide there where you showed the YAML like definitions of your benchmarks. Like, there's 3 parts in there. It was like warm up, something, and then iterations.
Yeah.
There it goes.
Yeah.
So how are you deciding how long is a good warm up? How long is a good time to? Actually, what does measured do again?
So warm-up is warm-up, so
yeah.
That measured is, we're benchmarking, so we're not just benchmarking once, we're benchmarking a couple of times the same exact work.
Number of times you run the benchmark.
And then taking the average.
Sure. So how are you deciding what's a good number for those parameters? Like what's your heuristic for deciding, oh, this one should be 3, this one should be 1, and that sort of thing?
That's a really good question. So because I'm the only one who has implemented this so far, I chose this based on how long operations took and how many times I would have to do an operation to get something significant, some kind of significant number. I didn't want it to be too small, because if you have the operation take such a small amount of time, system noise will get in the way of that. So you want to do the operation a number of times and then take the total time of that run. So it's kind of a compromise between running it 1,000, some really small operation 1,000 times, and running it only once. So you try to find a middle ground. So to answer your question, I made this up based on me running the test and seeing how many times I have to iterate on this operation to get something interesting and measure something significant, not just, I don't know, the parsing of the hash or something, or the serialization of the hash. But I do think that when other clients end up implementing this, we'll have to adjust these numbers based on how other languages perform. And that actually brings up a good point, because I don't even know if the numbers should be the same for every language, considering how fast some languages are versus others.
And the warm-up will be different for
I think the warm-up is less important to have everybody be consistent on. Like, if you think about it, the point of having this is so that we have a consistent results document. And I don't think we'll really be querying and looking for comparing how many times people warmed up. It's just really to like document that. I think it's so also the point of the benchmark is not really to compare clients to each other. It's to compare your code over time. So warming up is important for, if you think about it as a vertical, like a single client. So if I change my warm-ups, if I increase it, and then I see my performance go up a lot, that's an important number for me to know. Because I say, oh, okay, like if I warm up if I do this operation many more times, the performance will be twice as good. So, yeah.
Thank you.
Okay. Thank you very much for your attention.